Hello friends, let us discuss today the protections used for the transformer in power system. As transformer is the very important device in the power system, so various protection schemes for power system transformers used. Some of them are differential protection, overcurrent and ground fault protection, then gas pressure relays, oil and winding temperature devices. Now here in case of transformer, let us see the application of differential protection to the transformer. Now already we discussed about the bus differential protection. In that we saw that we compared the current entering the bus with that leaving the bus in order to detect the fault. With transformer differential protection, we use the same principle, however we must make a few changes to adapt the principle for use on transformers. Because the transformer primary and secondary currents are not same, that depends on the transformation ratio. So the CT ratios on the transformer primary and secondary sides must be chosen to match the transformation ratio. The CT secondary windings are usually delta connected for a star connected transformer winding and star connected for a delta connected transformer winding. This is to accommodate the primary to secondary phase shift. Some accommodation must be made for the transformer tap changer, which of course changes the primary to secondary ratio of the transformer. Some accommodation must also be made for the magnetizing inrush current which flows when the transformer is energized. This inrush current can be as high as 10 times the full load current of the transformer and flows into the transformer but not out. Now here note that with modern microprocessor based transformer protection relays, it is usual to connect the CTs in star or delta on both the primary and secondary sides of the transformer. The transformer winding configuration is programmed into the relay and any phase angle shift is taken care by the relay microprocessor. Now here differential protection schematic diagram for the transformer is shown. The CT ratios on the transformer primary and secondary side, that is this and this one, are chosen for current balance with the tap changer in the mid or neutral position. As the tap changer moves away from the neutral position, the unbalance between the primary and secondary CT currents increases. The transformer differential relay is designed specially to accommodate this mismatch in the primary and secondary CT currents. The transformer differential relay has both restraint or biased coils and operator. These are the restraint coil and this is the bias coil as shown in the figure. The differential current flows through the operate coil to make the relay pick up. Now differential current flows through the operating coil so that the relay will pick up, and through current falls through the restraint or bias coil and tends to make the relay restraint. So let us see in details. Now first let us see the out of zone fault, that is external fault, when the transformer experiences the external fault with differential protection. If there is an out of zone fault as shown here, when the tap changer is away from the neutral tap, then the through CT secondary current flowing through the restraint coil will overcome the tendency for the relay to operate by the spill current flowing through the operate coil. The differential relay will not operate for this out of zone condition. So here if we see, these are the CTs connected, this is the external fault, so the fault current is feeding can be sensed by the primary of both the CTs, and accordingly if we observe here, the current flowing through the restraint coil is only 3 ampere for the out of zone fault, and that much taken is care in case of differential protection that the current we can set for the operate here. So for that 3 ampere the differential protection will not work for the through fault. Now let us see when the fault is internal, that is when the fault is in zone fault as shown here. Now see, for the in zone fault shown, the current through the operate coil is very high, that is if we see the current flowing through the operating coil is now 37 ampere and the net restraining current is low. The differential relay will operate this in zone fault. Now when a transformer is energized, there is a magnetizing inrush current which can be as high as 10 times the full load current of the transformer. This high inrush current lasts for only a few cycles. However, it can cause the differential relay to operate because it has the appearance of an internal fault, that is current flows into but not out of the transformer. So this inrush current is predominantly second harmonic. A filter is used to separate the second harmonic component and the output from the filter is fed into the restraint coil of the relay to restrain operation. This feature is known as second harmonic restraint and is incorporated into all modern transformer differential relays. On microprocessor based transformer differential relays, the restraint for magnetizing inrush is achieved in a different way. The shape of the waveform is analyzed by the microprocessor to determine if magnetizing inrush current is present. The operating characteristics of a transformer differential relay are shown here. Note that the pickup current of the relay increases with the amount of through current. This slope is shown here. Now here one thing is important. Because differential protection remains stable for through or out of zone faults, it provides no overload protection for the transformer. Please remember this. Now the other protections for the transformers are overcurrent and ground fault protection. Now overcurrent and ground fault protection is commonly used on transformer. This is either as the primary protection for smaller units or any unit without differential protection, or as backup protection or larger unit protected by differential relays. For transformers of around 10 MVA and below, primary fuses are normally used. It is desirable to set the relays or fuses as sensitive as possible. However, they must not operate for any tolerable conditions such as magnetizing inrush, cold load pickup, or any emergency operating conditions. The ground fault relays must be set above the maximum zero sequence unbalance that can exist due to single phase loading. Overcurrent relays or fuses must protect the transformer against damage from through faults. The setting should be coordinated with the transformer damage curve and with the relay settings on the adjacent element. When transformers are operated in parallel, it is not possible to adequately apply overcurrent protection for each transformer and also provide the necessary selectivity. The overcurrent protection for both transformers can operate for a fault on the LV bus of one of the transformers. It is usual practice to apply differential protection where transformers are operated in parallel. If overcurrent is used as backup protection on transformers operating in parallel, emergency overload condition must be taken into account when determining the minimum pickup settings. When one transformer trips, the total load is then carried by the transformer remaining in service. This can result in emergency overloading of this transformer of say 150%. It may be possible for the transformer to tolerate this emergency condition for about say 2 to 3 hours, providing a winding temperature of 105 degrees centigrade is not exceeded. During this emergency overload period, load shedding or load transfers can take place to bring the transformer load down to the nameplate rating before the windings become overheated. An overcurrent pickup setting of twice full load is often used to allow for this emergency situation. The next is restricted earth fault or ground fault protection. The figure for it is shown here. Ground fault protection for each of the winding of transformer can be provided by connecting the cities as shown here. For for delta and star connected transformer windings. This system uses the differential principle to detect ground fault within the transformer. Now next protection equipment uses for the transformer is gas relays. The accumulation of gas or changes in pressure inside the tank of oil filled transformers are good indicators of internal faults. As we know, gas relays are used to detect these conditions. A very slow buildup of gas can be caused by very low energy arcs and deterioration of insulation and core problems. This is known as gas accumulation. A flashover of arc within the transformer tank will cause a sudden increase in pressure and cause a surge of oil to flow in the pipe from the top of the tank to the oil conservator, and this is known as gas pressure or surge conditions. A single relay is used to detect these two conditions. The relay is mounted at the top of the transformer with a pipe from the relay to the conservator tank. Any gas formed in the transformer will collect in the top section of the relay, depressing the float. This registers on a gauge on the front of the relay and will indicate a gas accumulation alarm. This accumulated gas can be played from the relay for analysis. The very slow accumulation of gas may be tolerable operating condition with some transformers. A flashover in the transformer will cause a pressure wave to travel through the oil and will compress the flexible bellows in the bottom section of the relay. The air inside the bellows will compress and will cause the flexible diaphragm to actuate the micro switch to initiate tripping of the transformer. The relay described in this is the Buchholz relay. The Buchholz relay is mounted in the pipe work from the top of the transformer to the oil conservator tank. It is shown here. It has a gas accumulation feature as described. However, the tripping feature of the relay is somewhat different. There is a flap in the relay which deflects whenever there is a sudden flow of oil through the relay towards the conservator tank. On some transformers, the startup of oil circulating pumps can cause sufficient pressure change to operate the gas relay. This should be checked during commissioning test and corrected if necessary. Other sensing equipment in case of transformer protection are oil and winding temperature devices. It is extremely important that transformer temperatures be monitored and limited to acceptable values. The temperature of the winding insulation determines the lifespan of the transformer. Insulation temperature at the hottest location is known as the hotspot temperature, and it is the insulation at the hotspot which ages the fastest. The hotspot temperature is therefore the limiting factor in determining the lifespan of the transformer. For a typical transformer with paper insulation, let us see, if the hotspot temperature is kept below 90 degrees centigrade, the expected lifespan is more than 50 years. At a temperature of 110 degrees centigrade, the lifespan is reduced to 7.3 years. So transformers are usually equipped with device to monitor the temperature of the oil and the windings. The first device monitors oil temperature and is connected via a capillary tube to a bulb fitted into a pocket surrounded with oil. The winding temperature device is similar except that there is a heater in the pocket with the bulb. This heater is supplied from a CT which is normally in a white phase primary bushing of the transformer. This heating circuit is designed to simulate the temperature of the transformer winding. When the transformer is on load, the winding temperature device should of course always indicate a higher temperature than the oil temperature device. For transformers equipped with cooling fans and pumps, the temperature devices are used to automatically start and stop the forced cooling. They are also equipped to initiate an alarm and a trip for a very high transformer temperatures. Now typical settings are for 75 degrees centigrade start cooling, 65 degrees centigrade stop cooling, 90 degrees centigrade high temperature alarm, and for 105 degrees centigrade trip transformer LV breaker. Now transformer applications usually include a guaranteed temperature rise at specific transformer loads. As an example, a transformer with a nameplate rating of say 17.5 MVA. Now guaranteed maximum winding temperature rise of 55 degrees centigrade at 17.5 MVA. Guaranteed maximum winding temperature rise of 65 degrees centigrade at 19.6 MVA. The actual temperature of the winding insulation depends upon the ambient temperature. For an ambient temperature of 20 degrees centigrade, maximum temperature of the winding at a load of 19.6 MVA will be 85 degrees centigrade. Let us see the testing of transformer protection. The individual current transformer and the overcurrent relays are tested. The operation of the transformer differential relay is tested by injecting current into the CT secondary circuit. The basic pickup of the relay is tested by passing a current through one restraint coil in series with the operating coil. In order to test the restraining characteristics of the relay for through faults, two current sources are used as shown in the diagram. The pickup current I1 is measured for